Welcome to the General Chemistry 2 class. This section is on physical properties of solutions. This lesson is about the colligative properties of non-electrolyte solutions. Let's begin. In this lesson, we will describe the effect of concentration on the colligative properties of solutions. Colligative properties are properties of solutions that depend on solute concentration. These properties are vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. Recall that vapor is the gaseous form of substance that normally exists as liquid or solid at a given temperature. Vapor pressure is the pressure exerted by a vapor above the liquid or solid in a closed container. If a liquid solvent mixes with a non-volatile solute to form a solution, the resulting vapor pressure of the solution is lower than the vapor pressure of the solvent alone. A non-volatile solute is a solute with a very small vapor pressure compared to the vapor pressure of a liquid solvent. The lowering of vapor pressure is due to greater solute-solvent attractive forces compared to solvent-solvent attractive forces. This causes solvent molecules to have less tendency to escape into the gas phase. For a solution of a non-volatile solute, the vapor pressure of the solution is the product of the mole fraction of a solvent and the vapor pressure of the pure solvent. By looking at the graph, the observed vapor pressure of solution is predicted by the Raoult's law when the mole fraction of the solvent is high or the solute concentration is low. This means Raoult's law holds true only for dilute solutions. The increase in boiling point or boiling point elevation when a solvent is mixed with a solute is directly proportional to the molar concentration of the solute. In the given equation, Kb is the ebullioscopic constant or molar boiling point elevation constant. This constant is a property of the solvent. For boiling point elevation to occur, the solute must be non-volatile. Table sugar or sucrose mixed with water produces a solution whose boiling point is greater than that of water. With this, more serious burns can be caused by boiling sugar syrup compared to boiling water, although both must be handled with extra care. The freezing point of a solution is lower than the freezing point of the solvent alone. The strong solute-solvent interaction prevents solvent molecules from assembling during solidification. For the solution to freeze, a lower temperature is required. The lowering of the freezing point or freezing point depression in the presence of a solute is directly proportional to the molar concentration of the solute. In the given equation, Kf is the cryoscopic constant or molar freezing point depression constant. Unlike in boiling point elevation, it is not necessary that the solute is non-volatile for freezing point depression to take place. One important example that exhibits freezing point depression is the use of coolants or antifreeze in car radiators. One example of coolants is aqueous solution of ethylene glycol. The use of coolants prevents the freezing of water in the radiator during extremely cold conditions below 0 degrees Celsius. Osmosis is the process of solvent passage through a semi-permeable membrane from a solution of lower concentration to a solution of higher concentration. A semi-permeable membrane is a porous material that allows passage of solvent molecules without carrying the solute. To prevent osmosis, there must be enough pressure above the solution, above the more concentrated solution. This pressure is referred to as the osmotic pressure. The osmotic pressure for a solution with more molar concentration at a given temperature is given as follows. In the equation, R is the universal constant, which is equal to 0.0821 liter atmosphere per mole Kelvin. Looking at the equation, we see that the osmotic pressure is directly proportional to the solute concentration. The higher the concentration, the higher the pressure needed to stop osmosis. Osmosis occurs when a blood cell is subjected to environments whose solute concentrations vary from that inside of the cell. In a hypertonic environment, solute concentration is greater outside the cell. The osmotic pressure is greater from the inside, so water goes out of the cell, causing it to shrink. In an isotonic environment, there is a balance between the solute concentration inside and outside of the cell. The osmotic pressure is equal inside and outside. In a hypotonic environment, the solute concentration is greater inside the cell. The osmotic pressure outside is greater, so water enters the cell, making it swell. The equations for colligative properties shown are valid for solutions of non-electrolytes or solutes that do not undergo dissociation in water. Electrolytes behave differently in solutions as a result of dissociation into ions. With this, the extent of dissociation is taken into account in a calculation. A separate lesson discusses further the colligative properties of electrolyte solutions. To summarize, colligative properties are properties of solutions that depend on solute concentration. Vapor pressure lowering of a solvent occurs when a non-volatile solute is present. For dilute solutions, the vapor pressures of the solution is governed by the Raoult's law. Moreover, boiling point elevation is the increase in boiling point of a solvent in the presence of a non-volatile solute. Freezing point depression is the lowering of freezing point when a solvent contains a volatile or non-volatile solute. Osmotic pressure is the pressure needed to prevent osmosis, which is the flow of solvent from a solution of higher concentration to a solution of a lower concentration. Here are the references for this video. Thank you.